Hello, everyone. Good morning, good day, good afternoon. We welcome you today on our second ML Toolkit webinar. Here are some links about where you can download the projects which we would be talking about. And after the webinar, we will send you a presentation, and it would be also the recording of the webinar will be available on YouTube. So our guest speakers today, I think we have the most geographically diverse webinar for InterSystems community, because our guest speakers are Anton Umnikov, Senior Cloud Solution Architect, InterSystems, with us from Orlando, United States. Sergey Lukyanchenko, Sales Engineer from InterSystems, with us from Paris, France, and me, Edward Lebdyuk, also Sales Engineer, InterSystems from Moscow, Russia. And today, we are going to talk about ML Toolkit, AI/ML, and automating and robotizing AI/ML workloads and projects. Oh, one other note before we start with the plan. In your Zoom software, you have an option to ask questions by clicking chat, and some people already found this function. And if you have any question, please write them there in chat to organizers or to everyone, and we will answer them at the end. Okay, so back to our agenda. Yes, we'll tell you some news about ML Toolkit, what we are getting to, and show free demos about robotizing the use of AI/ML models. We'll try to get it all done in under an hour, and after that we will have a Q&A. So ask your questions. Okay, so some projects. We are all around the world. With a bank from Kazakhstan. They were on Global Summit actually, and we were presenting a session together. They're interested in forecasting next best payments, clustering their customers and so on, and they're doing with InterSystems machine learning toolkit. We already finished a discovery phase and are progressing with piloting of a recommendation system. In United States of America, a group of radiology centers, they were also with us on this global summit. We also done a session together. And they're doing matching for between different terminologies, which is a very challenging topic in between many different medical terminologies available today. Supermarket network from Hungary, also using InterSystems ML Toolkit to simplify data transfer, and they have a series of Python scripts and reports, and they're building a supermarket rating system. One of our application partners from Ukraine are developing their own master data management solution. It's already available as an offering, and one of the important parts of master data management is built in golden record. And they use ML Toolkit to do record linkage, to find links between different records, to unify them into a golden record. Last but not least, a big utility company from Russia is in a process of discovery. They are interested in clustering for their customers, clients, and we are currently in discussion of depth modeling proof of concept. These are some interesting projects which we are currently doing on InterSystems ML Toolkit. Some of them are in production, some of them are moving towards production usage, and some are just starting. So, well, here is a small update. All right. Before we move to the most interesting part, I think the demos, I'd like to talk a little about InterSystems IRIS and AI machine learning, and how can we help you to complete successfully your AI ML projects. First of all, InterSystems IRIS is a data platform, so there could be and usually are a lot of business data. If you're using InterSystems IRIS to connect different systems, it's a great place to start exploring the data you have available, because IML projects usually require a very wide array of data in large volumes. InterSystems IRIS makes it possible to robotize the use of IML. This is the main topic of our today's webinar. How can we build a model, but after we build it, it's not the end in itself. Working a model is only a part of a process, and robotizing it and integrating it into a transactional business process is maybe even more important, because we need we really need to get value from that model, and it is only possible if, first of all, we are always sure that it produces actionable results, and second of all, we need these results right now while we are doing our transactions, while we are doing our business processes. And InterSystems IRIS makes it possible to do exactly that. To do all that, we can build and execute models with Python and R programming languages, which are probably one of the most popular languages for developing machine learning, artificial intelligence models. And with that intro, I'd like to move to the first demo and to pass the microphone and the screen to my colleague, Anton. Anton, are you?
Yes, I'm there. Thank you very much, Eduard. Let me start with talking to you about AWS SageMaker, and you'll get in a second why I'm talking about that. If you never heard about AWS SageMaker, it's Amazon Cloud managed machine learning platform and service. So it's fully managed, so you don't have to configure your instances. The instances are GPU enabled, so some advanced learning such as deep learning, CNN, RNN can be very effectively trained there. You have managed Jupyter Notebook. You have cluster of instances that you can spin up on demand. Wide variety of algorithms, as you can see there, and you can bring your own algorithms into SageMaker. If you're working in regulated industries such as healthcare, it's all HIPAA eligible and a bunch of other certifications across the industries. What's probably the most important thing that you need to know about SageMaker is that in SageMaker, you pay for actual training time only. You don't pay for these really expensive GPU-powered instances while you staring at your code and trying to figure out where in your Python code you made a typo or mistake, right? The instances has been provisioned on demand, and they're running for as long as your model need to be trained. As soon as training is done, instances shut down and you're not incurring any additional costs, right? So compare that to provisioning the instance with heavy GPU, so having in-house machine learning workstation with a bunch of GPUs. It's way less expensive, way less economical to use SageMaker for training your models. and then executing them either in the cloud or on premises. Right? So let me show you how it works from AWS perspective, right? So in AWS Management Console here, we have a whole bunch of services that AWS Cloud provides, right? Some compute services, storage services, and so on. You even have services that let you to communicate with satellites, right? And what's interesting, the approach I'll be showing you in a minute would work with all of the services because we will use standard AWS APIs, but the service we're interested in today is AWS SageMaker. So in SageMaker, you can have your notebooks, which is your managed Jupyter notebooks. You can have your training jobs. You can have your inference, which is actually running the model in the cloud. And as you can see from this dashboard, nothing is active right now, right? So let me switch to my IRIS terminal. As you can see, it's a standard IRIS instance. And in here, I do have already preloaded configuration, right? So the configuration in this particular case is a SQL statement that tells us what data do I need to pull in from IRIS to train my model, right? So basically arbitrary data that you already have in your IRIS instance can be used for training purposes. Then I specify the type of the instance that I'll be using to train my model. In this case, it's a CPU intensive extra large instance, like because it makes sense for that particular task. If we're doing something like deep learning with frameworks like TensorFlow, we'll be using GPU enabled instances, right? But the approach would be essentially the same. Here is I'm supplying what code I want to execute on that instance and some hyperparameters, right? Usually people who are familiar with machine learning at this point start to laugh because in more serious real life scenario, these hyperparameters can span few pages, right? In this case, we're just doing that just to show that you can pass hyperparameters to the instance. So now let me start this job. Right, so I'm passing this configuration JSON file to my AWS SageMaker, and yeah, job has started. So a whole bunch of things started to happening, but they're not happening on my instance. They all happening on AWS side. So if I'll refresh this page right now, right, I would see that one job is running, and this job is initiated from within my IRIS instance, right? So I'm running AWS job from within IRIS, right? This job would run for 3 to 4 minutes, depending on the complexity of the job, right? We can look at few jobs that we already completed prior to today, right? Let's pick this one, for example, right? So it's the same job. Training time is just 32 seconds. So it takes time to spin up the instances, to push the data from my local IRIS instance to the cloud. Overall time would be 3 to 4 minutes, as I said. But the time you'll be billed for, so time you will be paying for, is 32 seconds. Actually, Amazon would say, yeah, we have per second billing, but per second billing starts with 1 minute exactly, so I would be billed for 60 seconds, right? So a few cents here I would actually lose, but well, come on, I'm not paying for this expensive instance for hours and hours while I'm debugging my code, while I'm trying to optimize what I'm doing. I'm paying exactly for the time instance is being trained, and the billing component for that particular job would be a couple of cents at most. Right, and again, there's a big instance type and a whole bunch of other information. So if we go back to the PowerPoint, I would not keep you waiting for a few minutes to the job to complete it, but a log file would look something like this, right? We started the job, then we have a whole bunch of debug information, and finally job would be completed. and will incur billing for 36 seconds. Like what would happen after that, right? We will pull this model from AWS locally and would be able to execute it locally in IRIS. And this kind of scenario, this is what Eduard and Sergey would show you down the road, right? So how it works, right? You have IRIS instance that can be located either on-prem or in AWS cloud, and through standard APIs, we would be interacting with your S3 bucket, AWS SageMaker, and if we choose so, we would run this model in AWS. Alternatively, we can choose to run this model in on-prem, so this endpoint green box would not exist, right? If we run this model in AWS, the only ongoing cost we would incur is running the model in AWS. So next time we need to make a prediction, we'll make a call to cloud service, right? Or we can go into a model like this, where all we're doing at AWS is training the model, and then model is being executed locally, right? In this case, there are no ongoing costs, so everything is shut down, everything is gray, model is being executed locally. Now, the way it works is we're using standard APIs, using Python Gateway, standard AWS APIs to call SageMaker to interact with cloud storage, which is S3 bucket, and to move data to and from the bucket, between bucket and our local instance. What's important in this approach, right? And why the Python is so key to this kind of interaction. In theory, that all can be done through set of REST APIs that would let me from IRIS to call SageMaker to interact with S3 buckets, bypassing Python altogether. But it would be a significant development effort for me or for anyone else, because unlike Python, the REST API, even though it's documented, there are no really readily available samples or libraries that shows you how exactly you need to do that. So I'll just give you the few numbers, right? It took me around 3 hours to set up the local environment that would let me call SageMaker through Python from my local machine, right? The whole bunch of libraries need to be loaded, security and roles initiated. And after that, it took me just 15 minutes to translate the code from existing Python Jupyter notebook into the code I use from IRIS. If I am to translate this notebook into the REST calls, it would probably take me a couple of weeks. So the big enabler here, Python Gateway, not only it let you call arbitrary Python code from within IRIS, it opens up the whole community, the whole environment, all the source code, all the libraries that do exist in Python and that might be hard to find in any other language. So on this note, I would pass the word to my colleagues, and Eduard, your turn. Thank you very much.
Okay, thank you, Anton. I'm trying to share my screen. Just a second. Do you see my screen?
Yeah.
Okay. Yes, let's go to a second demo. It's about real-time predictive maintenance. This is a scenario from IoT industry. Let's say we have an engine. To be exact, it's a turbine. And any industrial big engine usually has a lot of sensors, which is always ready to supply you data in however great amount you want it. The trouble is processing. Our sample and simplified example, turbine has only 45 sensors. And in our data set, we already know the turbine state. To simplify matters, there are only two states available. Turbine either works and everything is fine, or the turbine doesn't work and we need to do something. So our goal from a more business point perspective is to predict engine failure beforehand and to run predictive maintenance, because as soon as we predicted that something would happen, engine would stop working, and we can actually do something with that, right? We can generate an email, we can create a human workflow task, well, do something. We can do predictive maintenance. That's the point, right? So here is how it's done in this example. We have InterSystems IRIS data platform, and inside that we have several components. We have Python operation, which is used to hold our Python code. And first of all, we have train process. Train process simply has all the parts. Let me show you how it looks for a second. Yes. All right. So you can check the Python code inside the process, what composes it, and it's used to train a model. We also have check service. Check service checks existing model predictions and validates them against true data. Eventually, in real life, we don't know the engine state at the moment, because if we did, we either find or already have a problem. We want to know it for future, for nearest future, or we have trouble getting it immediately. And so that's why we want to predict that. In check service, we correlate our predictions with the data, the true engine state we will get eventually. And based on that information, we can calculate the error level of our model. Does the model work, or if the model doesn't work, right? On the other hand, we have predict process, which we use to call the model and get predictions back. And we have predict service, which gets the data from outside, from our engine, and calls predict process to get predictions back. Now, so far it's all fairly straightforward, hopefully. Let's see how it all works. Check service detects when anomaly happens, when something changed, and retrains the model. And with InterSystems analytics, yes, we can see how it all works together. As you can see, our model starts just fine, but after a while, the error level percentage goes up. After a certain threshold, we can see it in a check service here. We have our threshold, so it's all easily configurable. And as soon as the model exceeds this threshold, the model is retrained. Right, so after we retrain the model, the error percentage goes down for a while. And after some time, because it's compressed, the data set we have is compressed across several months, so the engine wears out. And to get back to our presentation, this setup allows for AI ML robotization. We built the model, and it was done mostly manually with new QuickML, which will be soon available. you can automate that part too. But for now, we build the model by hands. And what's important, what's the point is that we are doing model validation and model retraining, and in some cases, in modern model hyperparameter training automatically. So humans don't need to perform this task anymore. We're all automated, and there's a process which automatically controls the accuracy of modeling results and adjusts the model accordingly. With InterSystems IRIS, you can easily implement solutions of this scale. If you're interested in this demo, at the end of the presentation, I will tell you how to reproduce it. There are several very simple ways. But now, with that said, I'd like to pass the screen to my colleague, Sergey.
Thank you, Eduard. And I'll pick it up from here to basically to continue your story, Eduard. Hopefully my screen is seen now.
I see your screen, yes.
Perfect. By asking several questions. So, for example, what would happen if we, because what we've seen in the previous, in Eduard's demo, the previous demo, we've seen that we can automate and actually orchestrate using the IRIS platform capabilities the running of ML content. What would it be if the external environment becomes really stochastic, really unpredictable? So, for example, we may have enough training data for the moment. The next moment, something drastically changes in the nature of the data, and we need to retrain. Not because the error goes beyond the limits we expected to go, but it's just the pressing requirement of the external environment that we train on something that represents this environment fairly. What happens if we all of a sudden got more training data in one training run that we expected, and then we don't have time to actually to get back in time to continue our prediction work? What happens? And there are many other possible situations that may arise in the real world, especially if our email is embedded in highly dynamic processes, real-life processes that may need a, I'd say, more elaborated approach to its robotization, and that's where we start speaking about actually splitting the previously monolithical analytical process, however nice and finished it may look, into a system of processes. So what we see in this slide, we see basically in the left part, where we're seeing the same model that Edward implemented. But this time our ask is to basically to make our platform, our AI platform, to recognize which portion of it is responsible for training, which portion of it is responsible for scoring, for prediction. Maybe there could be other portions to do the evaluation of freshly trained model and so on. So all of a sudden, our previously monolithical process becomes a set of processes. And in the demo that we're going to show you now, we actually presenting an example of such a system. We have a process that generates input data at regular intervals as files of regular length. We have a process called buffer that actually reads the input files and organizes queues to make sure we cope with data insufficiency, and we can actually maintain the most actual representation in that buffer of the training reality and of the reality that we're trying to predict. We have a process called analyzer that actually embeds all the Python content. We're using Python in this case, even if in that slide we've taken it from another example. We have, and Edward was mentioning it in the beginning, we can use both Python and R in the same system and the same process. And we have a monitor process that is responsible for monitoring the accuracy of the modeling done by analyzer. And actually, this process also manages the resulting queue. That means it takes into results the records that receive the prediction, and it deletes the old predictions and maintains a buffer, so to speak, of the most actual predictions. So what kind of ML content we are going to demo, and what are we going to envelope in this robotizer sort of template? We decided to make it sentiment analysis. So it's a classical machine learning task when you need to, by actually training your model on examples of positive and negative statements. You need to learn how to classify the statements. In this case, we are working with tweets, statements, posts from Twitter, social network. You need to learn how to classify the tweets that you don't know. You don't know. You don't see their labeling. Let's look at this through the model's eyes, and then what we further add to this example to make it actually resemble as much as possible a real-life situation when, for example, the sentiment analysis is not a one-off action, but it has to be a continual action. For example, you are sort of analytical agency and you're monitoring the internet, a number of sources, and you do the sentiment analysis on something that is, and you're also training your models on something that represents the actuality of your current moment, but soon it may be necessary to refresh your training data, and in parallel, you also have to look at how accurate your classification is. In this setup, what we need to achieve, we need to not only do it once, but we need to start working with some minimum available information and do the first training, and then start predicting using that minimum training data set, observing the results we are receiving. Then if the results we are receiving are not within the threshold of the accuracy we want, then we start growing our training data set. We redo the training, start applying it. We see that we are able to achieve, we are able to obtain more predictions. So we work longer without dropping out of error thresholds. And then we repetitively, actually, we construct a system that, as long as it feels that the training data set is not enough, it refeeds it with fresh information from the external sources. And by that, it copes with the dynamics of the outer expression, outer environment. And basically, by this, it also self-monitors and self-regulates its accuracy. So with that, let's go to my system here. I'm starting by showing you, maybe in a static way first, the outcomes of the previous run of this example. So at least there will be 3 dashboards that allow us to be in a complete cockpit of what's going on here. So basically, we have a buffer control dashboard that allows us to see what batches of data to classify the unclassified tweets we are receiving. So those numbers at the bottom are the batches. The batches, one batch is 100 tweets. We see the average time it takes for the solution to insert this batch into the buffer, just for performance control. In case we're starting to get problems with performance, we'll be seeing it here. And we have a sort of preview of what we currently have in the unclassified tweets buffer. The unclassified tweets buffer is not the only one. We have also buffers for positively labeled and negatively labeled tweets. We just don't put them on the dashboard, but let's keep in mind that they also exist. We will have a analyzer dashboard to basically control the two crucial moving parts. In this example, we will be controlling the evolution of our neural networks. We'll be using the recurring neural net in this example. And by the way, this example has been borrowed. We didn't build it ourselves. We've been looking at the available things on the internet and took one publicly available example that has seemed to us relatively compact on the one hand, performant, and also interesting. So through that example, we have a capacity to actually to train a neural net, and we'll be controlling this neural net's progress as it's being trained, and we'll be controlling it by running a validation of the model implemented in the neural net. That means we'll be, in the end of each training, we'll be applying that neural net to its own training data set and measuring the accuracy. On the other hand, in parallel, the trained model is applied to the unclassified data from the buffer. And as we all see it, the accuracy received, even if our trained model on the training, on the evaluation of the trained model, it's done relatively good. So relatively good in this example is above 80% of the so-called area under curve. This is a well-known indicator to measure classification accuracy. And we'll take a look at the concrete examples of concrete curve classification, rock curves produced by Python as it works through that process. So we will see that the area under curve, the classification accuracy achieved during prediction, it could be lower, it could be higher, but sometimes it's mostly lower than something that we see at the outcome of the training process. So this is an important controlling mechanism here that automatically detects when the accuracy at prediction becomes below a certain threshold. And once the monitor process, the one that we've shown before, it detects that it dropped below that level. It may not detect, by the way, so we're not like monitoring each and every prediction result. We're doing some sampling, but when this sampling catches something that is really below, it initiates, gives a signal to the analyzer process in that system to do the retraining. So let's do this. Let's run this example. And so to prevent any surprise, before I really go into the monitoring process, I will be explaining everything using my tables here. It will be a short initial period when I'll be forced to use those tables because my dashboards will start working only when I start the monitoring process. But that will be short and probably also informative. So what I'm doing, I'm starting first the generator process to start generating the input data for the system. Sending it a simple message. And I don't need to follow it anymore because this is a perpetual process that will be working now permanently. I have a queue monitor here in the system in IRIS platform that just tells me that the generator is working fine. So to check it, I go into my working directory, to my file system, and I see that out of 3 big sources of actually source input data, it has taken 3 chunks of standard size and generated three input batches that are waiting for being bufferized into my agentized system. I'm speaking of it as an agentized system because each process in that system, there are 4, is an absolutely sovereign agent working according to its own objectives and its own criteria. So what I need to do next, I'll start the buffering. Oops, start it. Go to my queue monitor. So I see that there are now 2 processes, the data generator and data buffer, that are running. Basically, now on the start, it has deleted everything from the previous run, so all the buffers have been nullified. And then behind the scenes, it's now refilling the labeled data. Why? Because I'm going here to my analyzer process, opening it up a little bit because there is no initial model, and before it will start doing anything, any predictions, any scoring work, it will need to train the initial model on the minimum available volume of data. So for that, it will need buffers refilled. So now I'm checking back. I see that my buffer of unclassified records is being progressively filled out. In every batch, there's 100 records. The label data, positive tweets and negative tweets, have been already filled. All right, so it has filled 10. It had filled my unclassified tweets buffer. We have previewed 10 batches for this buffer's depth. So now, what I can do, I can now proceed with starting to do the first model training, and I'm selecting the analyzer process. Click on test as with the previous two ones, and invoke the testing service, and leave it working. So now I'll just have a quick check that my 3 processes have started. You've seen that it in front of the analyzer process, there was quick 1 shown, and then it was been replaced by 0. Why? Because now analyzer process is starting to interact with Python, and you see that Python operation is now active. So it's doing actually the training work and creating for us all the nice layers of that sentiment analysis pies that involves vectorization, that involves the neural net training. So let it do that work quickly. It works. The first training is usually quite quick. Let's see some accuracy metrics is the outcome, and I'm waiting actually for it to give me the first area under curve. So this is the area under curve for the training, for the first training on the 10 batches, only 10 batches of labeled data. Not so bad, but also not so good. And with that, it starts doing the prediction work. So all the prediction outputs are being, we don't actually need to put that on the file system, but I'm doing it for better visualization. So I see some results here. But I can also track those results in the tables of the solution. So I see that 7 batches have been from the unclassified records have been scored. On the left, you see the results of the training accuracy under curve, and on the right, it progressively doing the prediction work on the first 10 batches of previously unclassified data. So now I'm at the point when my system of processes has run the prediction for the full buffer of the unclassified records. So the buffer has been refilled. You see that the number of the batches has shifted by 10. And to have it work further, so what I need to do, I need to start the monitoring process. So this process has not been yet enabled. And once I start it, it will start removing the data from the monitoring queue. So the monitoring queue, I'm refreshing it. You see that what was previously in the buffer is now moved to the monitoring queue. There are 10 previously buffered batches which are now in the monitoring queue, and they have been completely monitored. I see it from the table here. So the AUC, the area under curve, has been calculated for each of those batches. And also, when the monitor will be receiving the new records from the buffer, and it will see that the accuracy is not enough, it may start, and it will start, I know it from experience, it will start another training, but this time, the second time, it will import another 10 new batches of labeled data to make its accuracy progress. So let's invoke that. So I'm going to my production, click on tests, and I'm starting the monitoring process. So I'm checking here. Now I have my 4 processes actually collaborating. The full system is now in full, going full vapor. So what's happening now, I can better take a look at my dashboard. So basically, I see my buffer. I see the buffer of the unclassified records, unclassified tweets being refreshed. I see the outcome, those 76 something area under curve, the results of the first training shown as the horizontal line because there was only one training, and in parallel, there's prediction that is being done. And to make things a little bit more difficult for the system, we programmed it, we have parametered it in such a way that no immediate retrain will be made. It will have to, after each training, it will have to fully renew the buffer. So it is now rebuilding the buffer, but now it has touched at the 20th batch. It has seen that the accuracy is really at this batch that it starts controlling, get back to controlling the accuracy. It's below the 80%. The area on the curve as the result, as the outcome of the prediction, is now below 80%. So what's going now? Now it's, and you see that retrain file marker here in the working directory. It starts repeating the training. And it's repeating the training, as I said previously, by adding more batches in its training data set. So previously we've seen only 10 here. It has added another 20. So basically the purpose of it is to see in the end that we are achieving a better outcome because of actually extending our training data set. So let's take a look here. It'll take us some moments to complete the training, and we will just witness that the accuracy has gone up. And that will be probably enough for us to understand the principle of what we are achieving in this example. I'm just waiting for it to finish. So it's finished. See this little slope. So that means that after our second training, the accuracy obtained on the training results evaluation is now above 80%, which is promising. And we also see that the prediction accuracy for some lapse of time is going up. Going up, good. Going slightly down. While it's working, we can also observe the classification results. So as it works, as it classifies our previously unclassified records. So each of the tweets is receiving sort of score, the probability of it being positive or negative, and in the result monitoring dashboard, we actually see the two disjunctive sets of tweets that have been classified. In the first case, positive, and the numbers are green, and in the other case, negative, then the probabilities are shown red. And those are in permanent update because our results buffer is also updated, and it's the old records are being removed, the new records are being fed. So by this, we are achieving actually live monitoring of the content that we are loading into that agent-based system. So basically, we've built a totally automated mechanism to control and auto-control its training accuracy, and to basically to acquire unclassified records that need classification, something that probably would represent a newer press and newer posts on the internet, and make the whole set of moving parts work together as a system, as an adaptive system based on the buffers. So that means that we are protected against some temporary loss of data. We are securing, by using buffering, we're securing the permanent running. Switching buffering. And buffering goes well, so each batch is containing 100 records. There could be cases when there are less than 100 records, when the system is unable to import some particular tweets due to inability to interpret some spatial characters and so on. But so far, so good.
We have a question about retraining, actually.
Yeah, let's go to questions. Eduard, sorry to interrupt. Please repeat the question.
Yes, the question is, so when it saw that on batch with size 20, system decided to retrain.
Right. When it has seen it?
When it saw that on batch with size 20, the system decided to retrain.
Mm-hmm.
I think it was more about the number of, no, can you go back to your previous? I think it was about the generation. You have like batch 20 on the lower dashboard.
Yeah, you're right. The logic is like that. It does some training. Number one, in the very beginning, when you just start the whole solution, it trains a model because it needs something trained to work, and it does it. And it with that initially trained model, it does the prediction for first 10 batches in the buffer, regardless of the outcome, but regardless of the inferior actually accuracy. Then what we configured that instead of immediately switching to a retraining, it has to fully rebuild the buffer. So it adds another 10 batches in the process before it is allowed to retrain. We've done it in order to make this system not overreact actually on some temporary maybe losses of accuracy which could happen. But after it has acquired the 20th batch from the buffer, and it's seen that it's not, what was it, 70 something, and it has seen that it's not less than 80% the area under curve on prediction from that batch, the retraining has been triggered. So that's just everything. What you see here till batch 20 is according to the rules implemented for that system of processes. Further on, you see that without training, after the second training, the system has been running for 21 batch, which is also a small but progress. The higher the quality, the accuracy on the training will be achieved. So we have survived the third training here, and we see it on the graph. The longer, theoretically, it's not guaranteed because everything is stochastic here, and we cannot guarantee. But asymptotically, the more we repeat, the more we run, the more we see the distance between those trainings. That means that the quality increase, the accuracy increase we achieve on training will be converted into longer periods of uninterrupted prediction running. So that's the logic, just to give you a global view of it. Any more questions on the stack?
I do have another question. Once the RNN model is trained, would you save it to H5 format so it can be deployed? PMML doesn't support this exact type of a model. I would like to add a comment. I guess that in Python Gateway we offer a generalized object serializer, deserializer, so you can easily download your current state of your Python process into IRIS on disk. Well, into IRIS, not as a file. I mean, do parallelization this way, so you can both save and restore Python context from IRIS. The advantage of this approach is that you can do it to any object, not knowing the difference or what's inside, but we do support specific file formats. Sergey?
Yes, and it's a good remark from Edward. Actually, all we see on those working directories, normally it shouldn't be polluting the file system like here it's happening here. I'm showing now, if you see my screen, I'm showing you working directly from our Russian language, a prototype of actually doing practically the same thing, but with a Russian corpora of texts. And that prototype was implemented using TensorFlow and some other libraries to do the vectorization that precedes a neural net training. And there we were able to actually freeze out our embeddings in that format. And when the neural net was actually preparing to be trained, then the process was reading from those files the results of the embeddings. that is just a question of implementation. In our current demo that we're showing, we're not using it. We have a data set according to the authors actually of this scenario. It wasn't us, like I said in the beginning. They were gracious enough to do for us all those embeddings as a one single file with a TXT extension, but essentially it's the same as those H5. So it's read once at the start of the system, at the start of the analyzer process. And then it's being used continually all through the working of this system of processes. As far as my information goes, they have embedded some huge chunk of Wikipedia text in here. So this is supposed to be to be enough to cope with the vectorization of English language tweets for the purposes of this demo. Oh, this guy's doing all right. 40, yeah, you see it's growing. 41, now it's 63. So it's been running without training for 22 batches already. Initially it was 19, then 20, then 22. So it's going well. Any other questions?
We don't have any more questions so far.
We would like to remind. Well, maybe some of our audience are maybe trying to formulate a question. Eduard, let me remind you that your wonderful material is available publicly, and I'm showing it on the screen right now, so you can. Those that are interested and that would like to check it, you can download its Docker implementation. You can install the samples used in the demo shown by Eduard and some other demos on your host. See the links. You can play actually with the pre-configured demo of Eduard's using the link you see on the screen under the third bullet. So it's configured like a learning services, our learning services official site's course. So you can enroll for that course and actually enjoy a guided experience if you would really like for us to get some hands-on experience on the tooling itself. In addition, just to repeat the very first slide we've shown in the session today, we would like to attract your attention to our Open Exchange marketplace with specific pages in it dedicated to Python Gateway and R Gateway, the two solutions that we call a machine learning toolkit altogether. We would really like to encourage those of you that are not yet part of our machine learning toolkit user group to write us to the address you see on your screens, mltoolkit@intersystems.com. Your GitHub account details, actually the name of your GitHub account, and we would add you to that community. There are a number of useful materials that you can get from there. And again, Python Gateway samples, the link is also quoted here. You'll be sent all those slides actually after our session today as a single presentation. Any questions so far, Eduard?
I think there is currently
I think we're
have
done.
Only 1 minute left.
Mm-hmm.
So it's your last chance to ask questions right now, if anyone is interested.
And if not, again, robotize with us, implement distributed calculations. You've seen it from Anton's demo. That it's not just IRIS that is supposed to do all the robotization work. We can share the workload with a publicly available.
We have a question.
Yes, please.
Have you guys done time series?
The answer is yes, of course. We didn't put it on this demo because we kind of concentrate on the robotization today, whatever the ML content is. We could have done it actually with the time series example, but to give you a better view of it, if you Google through our learning services pages and you look for co-innovation in banking presentation delivered at our global summit 2019 in Boston this year, this September. You'll find a recorded session from there, slides plus voices. And among the examples presented in the banking context, there is also, we have given some details on the time series mechanism we've implemented for them that predicts the volume of transactional activity of payment processing partners of the bank. So please, if you don't find, you can contact us at the following email, mltoolkit@intersystems.com, and we'll be happy to send you individually the link to that recording. Returning to the thought I'm starting to develop, that about the robotization. So the purpose or the objective for today was to show that we can distribute the robotization, ML AI robotization work between the IRIS platform and the available cloud services, with IRIS in the driver's seat and actually orchestrating that process. Eduard has shown that we are able to orchestrate and to make work in a single analytical process. The mathematical modeling environments, like Python in this case, it could be also R, and we can take control of when and how would like those mathematical modeling be involved. And my demo was trying to show that we can also cope with the huge volume of data, the unpredictability of the external environment by actually configuring our robotized ML as an agentized system with multiple processes, each of them playing its role and actually guaranteeing a stability and let's say the robustness of our consumption of machine learning content, whatever it is, time series, neural nets, sentiment analysis, can be anything. All right. Unless we have any additional questions, Eduard?
No questions so far.
We're good.
I'd like to remind everyone that we will send you a recording and a presentation of this webinar. And I think our time is up for today.
Thank you. Please stay with us. Enroll in our future webinars. You are our golden audience. We value a lot your time and your attention to us. Thank you.
Thank you very much.
Thank you.